Hi, I'd like to show you a fully worked out homework problem from Chapter 4. Chapter 4 is an extraordinarily important chapter because it deals with open systems. And up to now, the chances are mighty good that most of your problems have been associated with closed systems. And in engineering practice, out in industry, in production, in many aspects of engineering, you're dealing with open systems generally operating in a steady manner. So let's get going with the analysis of a classic steam turbine. This is going to be problem 430 out of the textbook. And there's a little screenshot of what a steam turbine looks like. So let's go ahead and look at the problem statement. A well-insulated turbine operating at steady state develops 28.75 megawatts of power for a steam flow rate of 50 kilograms per second. The steam enters at 25 bars with a velocity of 61 meters per second and exits the steam turbine as saturated vapor at 0.06 bar with a velocity of 130 meters per second. It says neglecting potential energy effects, determine the inlet temperature in degrees C. Sounds pretty simple, only looking for one thing, right? Well, let's go ahead and get started. First thing, what does a steam turbine look like in the first place? It is quite possible that you haven't been exposed to steam turbines in your experience so far, but here's what one looks like. This equipment here is the steam turbine, and kind of notice the sort of conical shape of this steam turbine, and it's mechanically connected to an electric power generator. So for this application, the objective of a steam turbine is to drive a shaft at a known speed and torque in order to produce electric power. Here's what the cutaway view of a steam turbine looks like, maybe to try to explain a little bit more about that conical shape from inlet to outlet. So I've shown where the steam goes into the steam turbine, and it through a throttling valve. So this whole assembly here, the spring-loaded assembly and lever arm, that's adjusting a valve that adjusts the mass flow rate of steam going into and leaving the steam turbine. And that steam, what it's doing is it's flowing across a set of rotating steam turbine blades, causing the whole shaft to rotate. Now, so as the steam passes through each stage, each steam turbine blade stage, it expands. So the pressure of the steam drops, the specific volume increases. In other words, the steam expands as it's doing work on those blades. So thus the expansion of the steam. And that's how come the shape of the steam turbine is sort of a conical shape. Steam is expanding, pressure is dropping as you're producing power. And so then we're showing that the steam is going through the exhaust and it's exhausted down typically into a condenser. Now, so that's what a cutaway view of a real steam turbine looks like. What would your sketch look like? You're going to want to start with a sketch on all these open system problems, definitely. So your sketch should sort of look, it doesn't have to be a work of art, but it should sort of depict this conical shape area increasing as the steam flows into and out of the turbine. So your sketch needs to look like this. Oh, and let's see this block arrow, sort of a big arrow depicting W dot out, output power. So not W out, that would just be work. We're operating at steady state at a rate. So it's output power, W dot. Okay, so back to our problem at hand. So let's see. Let's look for keywords and clues. Well insulated. That's going to be a clue. So I've got insulation all around that turbine casing. That means we've got no heat transfer from the turbine casing to the surroundings. That's going to be critical for us. Operates at steady state. Okay, in other words, the rate at which steam is flowing into the turbine exactly equals the rate of steam flowing out of the turbine. M dot N equals M dot out. 28.75 megawatts of power. That's going to be critical for us because that's given. W dot then is given. The output power is a given number. And of course, here it says steam. So let's summarize what we see from our keywords and clues. The substance, it's H2O, steam. That is a phase change substance. And so for this solution, we're going to be using the steam property tables in your book. Open system, steady state, steady flow. So that's keyword, steady state. The type of open system is a turbine. And I've tried to give you a little example of what a turbine looks like. Okay. Let's see. Oh, in the problem, velocities are given. It's interesting that they're stated, and that tells me as an engineer, when I read that given information, that says if velocities are given, kinetic energy changes are going to come into play, and I should not ignore them. Okay, it develops 28.75 megawatts of power. That basically is saying W dot out is given. And then the well-insulated clue keyword that says this is an adiabatic process. In other words, Q dot N is 0. Adiabatic is a synonym for fully insulated. Oh, so you're asked to find, in the problem statement, you're asked to find T1, the inlet temperature of the steam going in. And so let's think about where you are in class. You've just finished chapter 3. And in chapter 3, you certainly covered phase change substances, but you also covered ideal gases. And you learned a really important thing about ideal gases, that P times little v equals RT, or you learned PV equals MRT, or some things like that. You say, okay, well, I'm looking for T1. Why don't I just use PV equals MRT? You need to resist that temptation, because in the problem statement, it said steam. And so when you see the word steam or water, all bets are off relative to the ideal gas equation of state. So you must resist the temptation to use an ideal gas relationship. Now, so you say, okay, darn it, I can't use that ideal gas relationship. Where do I start? What? And so you're going to, well, you'll start with a sketch, of course, and you'll get that sketch drawn, and then you start head scratching. Where do I go from here? I got the sketch. I don't know where to go from here. For these open system problems, you can just about count on just about always using the first law of thermodynamics to help solve the problem. And so I'd like to chase you to one of my videos that I call my first law of thermodynamics crash course. And you can find that on my YouTube channel under the fundamentals playlist. And so if you look at this, let's see, I'm trying to see how long this video takes. And I don't see on my slide how long it takes. Oh, 42 minutes. If you watch that, it's some tips on how to simplify, how to get the first law of thermodynamics in your head for open systems, closed systems, and different types of open systems. So I'm hoping that crash course video can help you out getting more familiar with the first law of thermodynamics. Okay, so back to our problem. Let's start with a sketch. And so here's what a good sketch looks like. I've drawn my turbine. I've drawn sort of a cross. That's insulation. I'm trying to show insulation of the turbine. And another thing I've shown on my sketch is Q dot N equals 0. So even though I've shown an arrow for heat transfer going in, I'm stating that it's 0. It's adiabatic. I've also shown a big arrow coming out of W dot and said what it is, 28.75 megawatts, given. I've written down all the given information at state 1. And so do you see that with the velocity written down, I can calculate the kinetic energy at state 1. And same thing on state 2. Oh, a really important piece of information in the problem statement that I didn't harp on was that it said saturated vapor at state 2, at the outlet, saturated vapor. That's really important clue, isn't it? It says that the phase of what's coming out at state 2 is a saturated vapor. It lays on the vapor dome right-hand side line. All right, let's see how the first law can help us. We're trying to find T2. I'm sorry. We're trying to find T1. That's what we don't know, T1. Okay. let's write down the first law and study what we can figure out from the first law. Steady state, steady flow, one inlet, one outlet. This should come to your head nearly immediately, I hope. Here we go. Q dot in minus W dot out equals M dot, there's only one M dot, M dot times the quantity, H2 minus H1, outlet minus inlet, plus kinetic energy 2 minus kinetic energy 1, outlet minus inlet. So let's check off things we know. Well, Qn, I've struck that out because it's adiabatic. W dot out, we can see with our sketch, we've got it. M dot, we've got it. H2, let's see, we can look that up. We can look up a value for H2 since we know the pressure and we know it's saturated vapor. Check that off. H1, we do not know. Kinetic energy 2, that's pretty easy. 1/2 V squared with units. And KE1, same idea, 1/2 V squared. Okay, so I do see at least that I can solve for H1 before I find T1. So let's continue planning. Let's look at a pressure volume diagram to reinforce what you know about this problem. Okay, here's our vapor dome for steam. We're going to start out at 25 bar, but we don't know exactly where we're starting out at. We do know that we're ending at a pressure of 0.06 bars and saturated vapor. So I can put a dot there. And so I know that I'm going to be coming downwards on the PV diagram. Pressure is dropping, okay? But because of some experience, some common sense, I'm just going to put a 1 dot somewhere up in this superheated vapor phase, okay? Now, in my case, I've solved a lot of these problems, both in class and in practice. So I have a pretty good idea that it's going to be superheated vapor. But let's remember what we're trying to find is T1. That's what we're trying to find. What is T1? So let's keep planning. We're looking for T1. Look, if I can find H1, which I think hopefully you can look at this first law statement that I've repeated. If I can find H1, I already know P1. That's going to give me two independent properties of state 1. And we remember from chapter 3, if I've got two independent properties for any substance, I can find all the other properties. So I'm going to find H1 first using the first law. Then I'm going to figure out what T1 is. Okay, so numerically, here's a restatement of the first law. Struck out Q dot in, W dot out, 28.75 megawatts. Gonna have to watch out for my units. M dot, 50 kilograms per second. H2, that's going to be a number, saturated vapor, that I'll look up at 0.06 bars. Okay. Kinetic energy, I'm going to calculate both of these with 1/2 V squared and get my unit straight. And so that's going to give me one equation and one unknown to find H1. All right, so let's keep plugging along. Let's work on H2 first. I'll go to the pressure table. I know P2, 0.06 bars. All I have to do, I know it's saturated vapor phase. Saturated vapor, all I've got to do is just go and look with my eyes and write down H2 is 2567.4 kilojoules per kilogram. That's Hg at P2. That's pretty easy. Next thing is those kinetic energy terms. And so recognize that you need to be pretty good at converting. So 1/2 V squared, that's units of V squared, meter squared per second squared. But I'm going to, in my first law, I've got to get to kilojoules per kilogram. You can derive, and here's the derivation. In a previous video, I worked folks through it, so I won't do it again. Recognize then that the conversion, the unity equals 1 kilojoule per kilogram divided by 1,000 meters squared per second squared. So that's your conversion factor. 1 kilojoule per kilogram equals 1,000 meters squared per second squared. So you're going to use that in your first law to keep your units straight. And if you'd like a little bit more about that, a little commercial here is if you go to my YouTube channel, Fundamentals, if you look at Working with Units Part 2, that's where I give you some really nice details about kinetic energy units, both in SI and in English when you have an English problem. All right, so now back to our problem at hand, numerics. Okay, I'm going to write down, I looked up H2, 2567.4, just showed you that. I'm going to write down W dot out is 28.75 megawatts, but when I study my first law, I see that I've got to have W dot out in kilowatts or kilojoules per second, kilowatts, kilojoules per second to keep my units uniform. So in my work, I simply slip the decimal point 3 places to get 28,750 kilowatts W dot out. I wrote down M dot, 50 kilograms per second, given. I wrote down my two velocities, and I calculated the kinetic energy, 1/2 V squared, and then divided that by 1,000 to get kinetic energy terms in terms of kilojoules per kilogram. Here's H2 from above. And so now I go back to my first law. So in my work, I'm going to refer back to my first law to solve flat out for H1, numerically solve it, 3148.99 kilojoules per kilogram. So that's H1. And then I wrote in my solution, I wrote down P1, 25 bars, and I circled those two independent properties. So if I've got two independent properties, I can get all the other properties at state 1, and I'm asked to find T1. So that's a little bit of a trick in this problem, very common on quizzes and tests. Okay, state 1. We need to verify that state 1 is superheated vapor phase. How do we do that? So I drew my PV diagram, and just because of some experience of myself, I said, I've got a sneaky suspicion that state 1 is going to be a superheated vapor. And I can confirm that. If I go to my pressure table at 25 bars and look over here at Hg, I see I've got 2803. And my H1 is 3149. So if my enthalpy is greater than Hg, that verifies that my phase at state 1 is a superheated vapor. So that's kind of an important check in a good quality solution. State 1 phase is superheated vapor. Okay, so I'm looking for T1. So I will go to my superheated vapor tables in the back of the book. Looks like table A4. And I got a pressure of 25 bars, and I look, uh-oh. In my book, I've got a pressures at 20 bar and pressures at 30 bar, but I don't have anything tabulated for H at 25 bars. That means I'm going to have to do like a double interpolation. I've got to interpolate between these two pressures to get numbers that correspond to 3149. So do you see, if I look over here, here's a range. 3149 is somewhere in there, and 3149 is somewhere in there. So I've got to generate some numbers here that correspond to 320, 360, and 400. And so if you're taking a quiz or a test, and this is, it's possible, okay, it would pay you to write down T1 is going to be somewhere between 320 and 400. At least you got that far. It might take you a significant amount of time to really hone in and interpolate to get T1. So at least you can write down T1's got to be somewhere between 320 and 400. Okay, if you need more tips on how to interpolate, if you limp through and, I got through it, I don't know how, and I'm going to forget about this interpolation stuff, you've really, really got to be good. You're going to be interpolating values out of the back of the book the rest of this class. And so I've got a video on how to interpolate, and that's also going to be in the fundamentals playlist, my YouTube channel. Okay, so here's what I did. In my solution, back to my solution, I wrote down in yellow cells, do you see, I wrote down my numbers for H at 20 bar and 30 bar, but I need to generate H values at 25. Well, 25 is halfway between 20 and 30, so it's easy to do this interpolation. At 320, so I go halfway between these two numbers, and at 360, I go halfway between these two numbers. And as I was working down the page, wait a minute, 3149, that sounds familiar. let's see. I got H1 equals 3148.99. Man, for an engineer, that's pretty darn close to 3149. And so, look, that's where I quit working. So I said, look, 3148.99 is close enough to 3149. I don't I don't need to interpolate anymore. I can see with my eyes that T1 is 360 degrees C. So that's my conclusion. And I wrote it down in my solution. So H1 equals 3149. So T1 equals 360 degrees C. And just to summarize, because a lot of times you get involved in these computations, it's hard to kind of remember what were you trying to do in the first place. You had a steam turbine. You were given the output power. You were given the kinetic energy changes. You were given the outlet enthalpy, the outlet pressure, and you found the outlet enthalpy, didn't you, using the first law? And so you're trying to find the inlet enthalpy and therefore the inlet temperature. So here's the summary. P1 is 25 bar given, H1 3149. You found that using the first law. And then T1 is 360 degrees C. You used interpolation to back calculate T1. And that's the solution. And so let's recap a little bit. Very, very good practice problem to get ready for quizzes or tests. You must start with a sketch on particularly these open system problems. You must start with a sketch. It pays to plan your work. Just starting crunching numbers, looking stuff up in the back of the book, not a good way to start. Start with the fundamentals. Write down the fundamentals after you've drawn your sketch and you're written. You've drawn down or depicted your given information on that sketch. Start with the fundamentals. In this case, the first law saved the day for us. Blindly using formulas in the book that might apply to your problem, that is a loser. That you're going to waste more time than you gain by looking for formulas. So thinking about fundamentals, what fundamentals can I use for this problem to get to the promised land? That's the winning recipe. Okay, another thing I did in my solution was check my units as I went along. I was careful to get my power units from megawatts into kilowatts, kilojoules per second. And I had to be careful to get my kinetic energy terms in terms of kilojoules per kilogram, not meter squared per second squared. And so you saw that at the end of my work where I was clearly stating my results, I expressed my results including units, not just numerical values. And let's see, I need to quit sharing. Oh, here we go. I always get tripped up trying to figure out how to stop sharing. So that's it. I hope that I've shown you how to analyze an open system phase change substance like steam, steady state, steady flow. Hope I've showed you how to solve a problem like that, start to finish, and nearly always you're doing something with the first law of thermodynamics to get that problem solved. So practice this on your own, and good luck in your Chapter 4 problem solving.